Hi there, welcome to another Leetcode solution. In this video, we'll be looking at Leetcode problem 270, which is closest binary search tree value. It's commonly asked in interviews in FANG companies, and if you look at the companies list here, it's quite frequently asked in Meta. Particularly recent interviews has been asking this. It looks like since it says 0 to 3 months, that means it's quite recent. All right, so let's read the problem. It says, given a root of a binary search tree and a target value, return the value in BST that is closest to the target. If there are multiple answers, print the smallest value. All right, so they have also given an example. We have this tree here. The target is 3.71, and then they are expecting the output 4. Let's see why 4. So if you look at our values in the node, in the tree here, it's 4, 2, 1, 3, and 5. So 3.7 is indeed close to 4 because it's just having a difference of 0.3, and the next closer item that we can see here is 3, but it's 0.7 apart from the node or the target. So that's not our answer. The answer should be 4. There's another example here that they have given a single node tree and the target is 4 because there's no other closer value in the tree. We'll end up returning 1. So how do we solve this? So let's look at the first graph here. So let's say because it's a tree, we'll have to traverse its nodes. So let's say we start with 4. We check if we check its distance and from the target, which is like 3.7 minus 4, or the opposite, 4 minus 1, 3.7. We get 0.3 as our distance, and then we go to next one. We get 1.7 as difference. We see it's not lesser than the last distance we got. Then we continue further. We check 1 because we know that on the right side, if you go, it's not going to give us a better distance because the value is larger than our last distance as well as the last node. So the chances of getting this value smaller here is very much low. Or actually, it's not even possible. So let's try to write this problem solution here. So let's say we got our root, and then there is obviously a target value. So we can say, let's assume that the closest item we got so far was the root node itself, because we'll be comparing it with the next ones. So we initialize the closest as the current root node, then we start traversing through the nodes. So let's say while root, we check the current diff, which will be the absolute difference between the root.val and the target. So remember, we are doing an absolute difference here because the value could be lower than the target or it could be higher than the target. So that's why absolute distance. In both cases, we care about the difference, not the absolute positive or negative value, right? So yeah, we got the current diff. Now, because we don't have any previous diff to compare here, we can initialize the previous diff as minus or basically positive infinity. So let's assume our diff was initially set to infinite value, which would be always higher than whatever diff we get here. So we got our previous diff, we got our current diff. So whenever we get a lesser diff, we want to update our value to say it's the closest one, because that's what we are looking for. So if current diff is less than previous diff, we update our closest value to say root.val, because that's the value currently we have. Then there could be one more case when our both differences or the current diff is equal to the last diff. So let's say in this example, let's say we had a target of 4 and then we minused it with 3, and let's say minused it with 5, we could have got the same difference of 1. So in that case, we will need to handle that as well. So if our current diff is equal to previous diff, actually double equal is here, and in that case we can say whatever is the minimum value between our last closest, and current root.val is our closest value. Why is that? Because we are saying here, or they're asking in the answer here, if there are multiple answers, print the smallest value. So that's why we are doing a minimum here. So we got two values, that is root.val and the closest. So we got the value here, which is the minimum. We store it here. And remember, we also need to update our previous diff once we calculate the current diff, because we found a new lowest, need to keep track of it in our previous diff so we can compare it next time. And remember, because we also need to continue traversing the nodes after this, we need to update our root. So we can say our new root is equal to root dot left if the target is less than the root dot value we had, else we go to root dot right, and in the end we return the closest value whatever we have. Right, so let's give it a walkthrough, because that's what your interviewer probably expects when you give interviews in one of the big tech companies or any company which is expecting you to understand algorithms and the solutions properly. So let's put down our variables here. We have the closest variable, then we have the previous diff, then we have our root, and yeah, that is it basically. So our closest value will be set to the root of the tree first. So let's say we have this example which has the closest set as 4. Then we have previous diff set to infinity. Then we have our root, which is also equal to 4, which is the root of the node now, root of the tree now. So whenever we have a root value present, we calculate the diff. So yeah, obviously we need to keep track of current diff as well. So what is our current diff? So it's it's an absolute value of target minus root dot val. So our target here is given as 4. Actually not 4, it's 3.7. So let's just say 3.7 for now, and we have to minus it from the root value we have. So yeah, it will give us 0.3 for now, let's say, because it's an absolute value. Right, that's our current diff is updated to that. Then we are checking if current diff is less than the previous diff. That's true, so we update our previous diff to 0.3, and we also set our closest value to root val, which should be the same in this case, 4. And then we continue to do the same thing. In this case, this is a very positive scenario where we got our latest value or the least value difference value at the root, but we are still continuing the loop, right? So we have our closest value is to set to the root value. Then we also check if current diff is equal to previous diff, which is not the case in this step, so this won't trigger. Then we check whether we should go left or whether we should go right. So we should go left when the target value is less than root dot value. So in this case, the target value was 3.7, and it is less than the target, or actually it is greater than the root value. So that's why actually it was less than the root value. So we go left in this case. So we go to 2, we update our root to 2, then our closest remains the 4, then our previous diff is updated to this. Current diff is changed now because we are going visiting 2, so 3.7 minus 2 would be 1.7. And similarly we continue going through the root. In this case we'll be going, because our target was greater than 2, it would be going to the right side of the tree. So we went to 4, then 2, then 3, and yeah, that is it basically. We iterated through the height of the list once, and that's why our time complexity would be O of h, and our space complexity will be O of 1 here, because we are not really using any extra space apart from tracking the variables for the result. Yeah, this is basically the solution, and if we try to run it, we can check if there are any mistakes we have done. So let's just try run through it. Closest is set to current root. We have initialized previous diff is equal to float inf. Then we have while root current diff is absolute of target minus root dot value, which is fine. If current diff is less than previous diff, we update our closest, also set the previous diff. If else if we have the same difference, we use the lowest value amongst the two. Then we go to the left if our target was less than the current root, else we go to the right. In the end we return our closest. So yeah, this should work. Let's see. Right, yeah, it does work. Submit it. Yeah, it's, you can see it's a pretty good solution, beats 100%. And if you look at the time complexity, it's O of h, which is what we came up with. So yeah, that's it. Thanks for watching.